Okay, here we are with the part 2 of the Module 7 lectures, the organic chemistry lectures. We're going to be talking about a couple of things called alkenes and alkynes. Now, you're used to, we've already talked about alkanes to a substantial, significant extent, and this is really not going to be much different. A lot of it goes along similar lines. There are some differences in the chemistry between them, but they're actually fairly similar. There are similarities, and naming them, you're going to get a little bit more. Actually, from now on, we're going to be seeing more definitive with regard to numbering chains, because these functional groups that we're going to be talking about define the start and end point of the various chains. You'll see what I'm talking about. Alkenes and alkynes have multiple bonds. Okay, ethine, which we normally know as acetylene, is used in welding, and there's a few alkynes in biological systems. There's not too many of them, but there are a few. And they contain double bonds and triple. Well, alkynes contain triple bonds. Alkenes contain double bonds, and they're called unsaturated because they do not contain the maximum number of possible hydrogen atoms. If you remember ethane, C2H6, it's a 2-carbon chain with all the remaining valences of carbon containing hydrogen. So there's 6 hydrogens there. Ethene, also known as ethylene, is C2H4, and it has a double bond, and you'll see these things shortly. But we got ethylene coming up right in the next slide. They do react with hydrogen gas to increase the number of hydrogen atoms. They add hydrogen with a catalyst to become alkanes, but they have some interesting chemistry in their own right. And there you have ethene. The carbon-carbon double bond system is, you remember, if you take either of the carbons, they both have 3 electron groups, and that makes them trigonal, planar in structure. So the bond angles around those doubly bonded carbon atoms are around 120 degrees. These are single bonds. There's free rotation around single bonds, but there is not free rotation around double bonds. They're fairly rigid, and we'll see. There's implications to that. We'll see shortly. Then ethene, that's a very important one. You make polyethylene with it. But also it's a plant hormone, and it's involved in fruit ripening. So it also accelerates the breakdown of cellulose in plants, which is why you have flowers wilting and leaves falling from trees. Alkynes have triple bonds, and the geometry around the carbon atoms involved in a triple bond is going to be linear because you only have 2 electron groups. Remember, one of the electron groups has 3 pairs, 6 electrons, but it's still grouped together in a single unit. So these things want to get as far apart as possible, so they get 180 degrees. So the carbon-carbon triple bonds are linear with bond angles of 180 degrees. Okay, and now, right off the bat, we have a learning check. So identify the following compounds as alkene or alkyne. Remember, ENE is a double bond, IYNE is a triple bond. So I just gave it away. A is an alkene, and you will be able to discern for yourself that the name of that one would be 3-octene, and the other one is going to be, that would be 4-propyl 1-octyne. Okay, so we'll talk about this. Just identify them as the alkenes or alkynes. So anyway, they don't really give the names there, but you will be able to name these things shortly. And just remember, the alkene is a double bond, and alkyne is a triple bond. And sometimes you can have double bonds and triple bonds in the same molecule. So we're not going to get into that. we're mostly interested in your knowing the functional groups, a little bit about it, and how to name these compounds. So that's really all we're really looking for here. So this should be a reasonably easy module, although you do need to be able to see things in 3 dimensions, what's called spatial thinking or something like that. You need a lot of that in organic chemistry, but let's go on. Naming these things, naming is similar to alkanes, although we have another little wrinkle here. This is a really little wrinkle. You change the alkane name, replace the ending ane with ene, ene. Cyclic alkenes are named as cycloalkenes. Cyclic alkenes are named as cycloalkenes, like cycloalkanes are named as cyclic alkanes are named as cycloalkanes. And here we have some examples of these. Comparison of names for the alkanes, alkenes, and alkynes. So you see ethane is 2 carbons and saturated. It's ethane, it's an alkane. Ethene has 2 carbons, but 2 less hydrogens, 2 fewer hydrogens than ethane. It is ethene, that's an alkene, and you remove 2 more carbons, or 2 more hydrogens rather, and you have ethyne or acetylene. Of course, if you remove 2 more hydrogens, you're going to have carbon, which is, actually, you're not going to have there's no such thing as a 2 carbon atom molecule of carbon. So, but you're going to have essentially carbon. Ethane, ethene, ethyne, same way. Propane, propene, propyne, and you see the line drawings there. You see the condensed structural formulas and the line angle formulas. This is the way they're represented. There's no tricks to it. There's no surprises there. This should be fairly straightforward. All right. Now we're going to have to look at some IUPAC names. And there we have 2 compounds, one of which you should recognize as an alkene, and one you should recognize as an alkyne. Now, the way we do this is pretty much the same as what we do for alkanes, but there's going to be a little bit of a change. You're going to see this. You always look for the longest continuous chain containing the prime functional group. Now, when we have alkenes and alkynes, the numbering is defined, it's fixed by the position of the double bond in that chain. Okay, so what we're going to see is that we're going to pick out the longest continuous chain, and you can count these things. If you count this 1, 2, 3, the A 1, 2, 3, 4, 5, one way 1, 2, 3, 4, 5. You've got a 5 carbon chain, and the double bond defines you want the double bond to have the lowest number. So you can see it's going to be on the 2 carbon, and you number through the double bond. So there's going to be carbon 1. Carbon 2 is going to start the double bond. Carbon 3 will end the double bond, and carbon 4 and 5. So you're going to have the methyl group here is actually going to be on the 4 carbon. So that's giving you a little bit of a change from what you remember of just put the substituents there and they all get the lowest possible number. Well, no, this time the double bond gets the lowest possible number, and the substituents are numbered accordingly. So this is going to be 4-methyl 2-pentene. All right. The next one, B, is an alkyne, and this one's going to be a little easier because there's no substituents. It's just a continuous chain. And the chain is 1, 2, 3, 4, 5, 6. The 2 and 3 carbons have the triple bond. So it's going to be what, 1, 2, 3, 4, 5, 6. Okay, 6 carbons. So it's going to be 2-octyne, and that's it. Okay, so let's see how that works out. See, 5 carbons, pentene. Name the longest carbon chain that contains a double or triple bond. You have 5 carbons for pentene and the 6 carbons for hexyne. Okay, so we have a pentene and we have a hexyne. But now, you number the carbon chain starting from the end near the double or triple bond. So that's something new. So whatever this thing is, whatever A is, it's going to be a 2-pentene. Whatever, you have a methyl group there. We have to decide on that later. So you see it's a 2-pentene and B is a 2-hexyne. There's nomenclature, in organic nomenclature, there's functional groups that have a certain priority. And we're not going to worry about that in this course, but if you could have a carboxyl group. Well, I'll learn what a carboxyl group is later, but that's a carboxylic acid and a double bond in the same molecule, and then you have to, and that's going to make it a little different because the carboxyl group is going to have priority over the double bond. So it gets kind of complicated, but it's systematic. The rules are understandable, but for now, we don't need to really worry too much about that. The basics of nomenclature is what we're doing. Okay, so you see it's 4-methyl-2-pentene and 2-hexyne. There's no substituents on that one. Cycloalkanes, you do it the same way as you did cycloalkanes. And now they have a double bond within the ring structure somewhere. And they are named by assigning the double bond to be between carbon 1 and 2. All right, so you see you have a methyl cyclohexene in there. There's a methyl substituent on it, and it's a 5-carbon ring, and it's an alkene, so it's a cyclopentene. And the 1 and 2 carbons are going to be with the double bond. The number of the methyl group, the number that you assign to the methyl group, is going to be, you assign it through the double bond. So this is going to be 3 cyclopentene. And by the way, if you put it on think about it, if that methyl group were actually on the carbon which is adjacent to the carbon labeled number 1, that would no longer be number 1. You have to go through it would still be 3 methyl cyclopentene, because you number clockwise instead of it's counterclockwise here. So you've got to be aware of the geometry of these things, and you have to realize that you can flip these things, you can rotate these things, you can reflect them. There's things you can do with them, and you have to be aware of those things. So the only other, you could have, if the methyl group were on one of the double bond carbons, then that would be the 1. That would be the 1 position. But if it's off of the double bond, then you have to go through the double bond. But I'm pretty sure what you see in this course is going to be where the substituents on an alkene tend to be off of a double bond, away from a double bonded carbon. But if there's any other, if we see them again, of course I'm going to point that out. Okay, so you name these things. Well, how do we name them? Well, one of them is pretty simple. It's a 6-membered ring, cyclohex something. You remember cyclohexane? Well, now we have a double bond, cyclohexene. There's really you don't need to put a number there because there's no substituents. Cyclohexene is cyclohexene. You can rotate this thing any way you wanted, and it would still be cyclohexene. The next one is a cyclopentene, but now you have 2 substituents. And remember what I said, to number the substituents, you have to number through the double bond. You have to proceed through the double bond. So carbon 1 and carbon 2 are always going to be the double bonded carbons in a cyclo something ene. So this is going to be 3,3-dimethyl cyclopentene, if you think about it. And you see that's what we get. Okay, so much for alkenes and alkynes. That was quick. That's pretty much what you need to know. You need to know what these things look like. You need to know how to name them. So if we give you a name, you're going to be able to figure out what it is. Anyway, so that's all for section 11.5. Let's move on to section 11.6. Section 11.6 introduces a little more of what we call stereochemistry. Now, I've probably used the term stereochemistry before, and you know that it's really, stereochemistry deals with the three-dimensional geometry of molecules. All right, we've talked about molecular shapes. We've talked about that, molecular geometry. This is a little bit different. Here we have, you'll see what I'm talking about. We have something called Cis-Trans Isomers. Cis, it's CIS, trans, those are from Latin, meaning the cis being the same side of and trans being the opposite side of. If you've read Caesar's Gallic Wars, you know about Cisalpine Gaul, which is that side of Gaul which is on the side of the Alps. It was actually in Italy. Transalpine Gaul is what's now France. It was over the Alps from Italy. So cis is the same side, trans is the opposite side. So if you think of a double bond, then they have these hands here in these orientations where the thumbs are on the same side of the double bond formed by the fingers. That's cis. Trans is on the opposite side. That's all there is to it, to the trans, cis and trans configurations. And what we're going to be doing here is draw the condensed structural formulas and give the names for the cis and trans isomers of alkenes. And of course, the line angle drawings also should come naturally with that. In an alkene, the double bond's rigid, as I mentioned a few minutes ago. It does not rotate. In alkanes, all the bonds can rotate freely, except, well, not in rings exactly. So you do have cis-trans isomers in rings, even in cycloalkanes, but we're not going to worry about them here. We're worrying about the cis-trans isomers in alkenes. Anytime you have a situation where, well, here we have a fairly simple one. There's 1,2-dichloroethene. Each carbon atom has two different substituents on it. You see, each carbon atom has a hydrogen and a chlorine attached to it. And since you have that restricted rotation, that hindered rotation, you can arrange the chlorines on the same side of the carbon atom of the double bond, or on opposite sides of the double bond, or the hydrogens on opposite sides of the double bond. When they're on the same sides, it's a 1,2-dichloroethene. When it's on the same side, it's cis 1,2-dichloroethene. When it's on opposite sides, it's trans 1,2-dichloroethene. So that's all there is to cis-trans isomerism. Now, if you have different substituents, if you have like a bromine, and one of the hydrogens is a bromine, and then you have complications. But there's a system for that, which we're not going to really worry about right now, which we're not going to talk about. What you're going to see in biochemistry is largely going to be cis and trans. So there's again, the cis and trans is a duplicated slide, but it's nice enough to repeat it. So you can make a double bond with your fingers, and both thumbs opposite, and they can be opposite, in which case they're trans, the same side, in which case they're cis. A lot of alkenes exhibit cis-trans isomerism. If you have just a straight chain, there I go with the straight chain, a continuous chain, unbranched chain that has a double bond other than on the end carbon. So you can think of 1-butene, think of a 4-carbon alkene with the double bond in the 1 and 2 position. Well, there you don't have cis-trans isomerism there because there's two identical atoms on the end carbon. But when you get to 2-butene, now you have a hydrogen and a methyl group on each carbon, so you're going to have the possibility of cis-trans isomerism there. And just as I said before, the cis isomer, the two methyl groups are on the same side of the double bond, and in the trans isomer, the alkyl groups are on opposite sides of the double bond. So there's those. Cis-trans isomerism, well, other forms of isomerism as well, will make a difference in how a particular compound smells. A cis isomer of a compound is going to have different properties than a trans isomer. You've heard of trans fatty acids not being good for you. Well, most fatty acids, double bonds in fatty acids, we're going to see this. It'll be coming up in another module. In fatty acids, unsaturated fatty acids, oleic acid, linoleic acid, linolenic acid, that kind of thing, the double bonds are cis. You have a trans fatty acid, you heat the thing up, and it's going to give you very different properties. And of course, trans fatty acids are associated with some bad things. So, also in the real world, these various you have these pheromones, and you see sometimes one of these pheromones is bombacol, and they say it's a sex pheromone produced by a female silkworm moth. It contains one cis double bond and one trans double bond. Now they don't really give you the exact configuration of this thing, but you will see that these isomers will have them. If you change the configuration around a double bond, it's going to the compound, if it has a strong smell, it's going to smell very different. And we'll see more examples of that when we get to mirror image isomers. But just be aware that orientation around the double bond is not a trivial thing. Naming these things is really simple. You add a prefix of cis or trans in front of the alkene name when the compound is a cis or trans isomer. So you have 1,2-dibromoethene. The cis version is cis 1,2-dibromoethene. Trans version is trans 1,2-bromoethene. It's as simple as that. We're going to do some examples here. Name each using cis or trans prefixes when needed. Okay. This one, you have A, B, and C. You have A, which is, as you see, there's a 4-carbon alkene. What would be the name of that? Think about it. B is a 4-carbon alkene. What would be the name of that? And C is a 4-carbon alkene. That one doesn't have any substituents. So, how are we going to name these things? Well, all of them, I think you can see, I hope you can see, that all 4 of them are 4-carbon alkenes with the double bond between the 2 and 3 carbon. 2 and 3 carbons. Okay, so they're all going to be 2-butenes. So the end of the name is going to be 2-butene. Now you have to worry about the substituents. Well, the substituents, C is no problem. There's no substituents. It's all hydrocarbon. But A has 2 chlorines. So how are you going to call that? Well, you're going to call it it's going to be a dichloro 2-butene. B is going to be a dibromo 2-butene. C is just going to be a 2-butene. All right. Well, the similar groups. Each carbon atom on each compound. Okay. The double bonded carbon atoms have a chlorine. Each carbon has a chlorine and a methyl group on it. So there's going to be. So which side of the double bond are the like substituents on? Okay, well, A is going to has to be cis. That's a cis 2-butene. So you have 2-chloro cis 2-butene. Or cis chloro one cis 2,3-dichloro cis-2-butene, or cis-2,3-dichloro-2-butene. The second one is going to be cis-2,3 or trans-2,3-dibromo-2-butene, and the last one is just going to be trans-2-butene. So you have two cis, two trans, or one cis compound. We're mixing these up. Okay, A is going to be a cis-2,3-dichloro-2-butene. B, look where it's trans because the like groups are on opposite sides, and so that's going to be trans-2,3-dibromo-2-butene, and then the C is just going to be trans-2-butene. So how did we do with that? See, it's sometimes you will see the cis inserted between the substituents and the sometimes you'll see the substituents between the cis and trans between the substituents and the actual butene. You see, they don't really put the 2-butene in here, except for trans-2-butene. You probably, I'm going to need to look into this because that doesn't really look correct to me. And you have trans-2-butene, well, then you should have trans-2,3-dibromo-2-butene and cis-2,3-dichloro-2-butene. So I'm going to take it upon myself to correct these here. Because there is such a thing as a 1-butene. The fact that it's cis or trans makes it somewhat redundant. There's only one butene that is going to have cis and trans isomerism, but it's typical to put these, to give the numbering in there. You could conceivably have a situation where you have a 1-butene with say a chlorine on the one carbon. So then you could have a cis 1-chloro-1-butene. But I think this was an oversight on the part of the part of Pearson. So that is the end of section 11.6. We're going to go on to section 11.8. We're skipping 11.7. So I'll see you over on the other side. All right, this is going to finish up chapter 11. We still have some things from 12 and 14, chapters 12 and 14. We'll get to that next. Aromatic compounds are another important group of organic compounds, and we need to know these things. They're very common in biochemistry. The non-aromatic compounds, which are called aliphatic compounds, and I think I've got a note there in a subsequent slide. But the little historical thing is in 1825, Michael Faraday first isolated benzene, which has a 6-membered ring with alternating double bonds and has a molecular formula C6H6. Now, a 6-membered ring with alternating single and double bonds like that has some very special properties, and we call these aromatic in particular because so many of them have very strong and often pleasant smells. Benzene actually has a fairly pleasant smell. There's another one, but you don't see that very often anymore. It's still used in some places, but toluene is one that you probably have smelled here and there. It has a very pleasant smell to it. And there's a few others like that. We're going to be talking about the benzene ring and naming aromatic compounds, drawing their line angle formulas. And that'll be pretty much it. Benzene's an aromatic compound, as we said. It is a 6-carbon ring. Each carbon atom has one hydrogen on it, so you see a couple of different structures there. We usually sometimes represent this with alternating single and double bonds. It depends on the who's writing, whether it's going to be alternating single and double bonds or that ring, that circle inside the six-membered ring. I mean, your text uses the circle, but they mean the same thing. You see the single double bond things. It's actually they're indicating that that's actually a hybrid. The actual structure of benzene is a hybrid of those two. It's sort of an average of them, which is why the circle. There's some with common names. Benzene's a common name. Toluene's a common name. Aniline's a common name, and phenol's a common name. It's not methylbenzene. It's not aminobenzene. It's not hydroxy benzene. So it's toluene, aniline, and phenol. And they have these names for historical reasons. The names have become ingrained, and it's a lot easier to just stick with those. In the case of these three, if there's only one substituent on the ring, that's not numbered. Same thing with cycloalkenes and cycloalkanes, and there are actually cycloalkynes, but they're very large chain. But they're much larger chains, and you really aren't going to see them in anything you're going to be doing. And when there's more than one substituent, benzene ring is numbered to give the lowest numbers to the substituents. There are some little wrinkles to that, though. Okay, with the dichlorobenzenes, you see it's 1, 2, 1, 3, and 1, 4. That should be fairly easy to understand. When we get to toluene, phenol, or aniline, when they have substituents, then it gets a little different. All right, you see 3-bromoaniline. Okay, for aniline, the carbon with the amino group with the NH2, that is the one carbon. Phenol, the one with the OH, that is the one carbon. With toluene, the one that has the methyl group, that is the one carbon. So you're going to give the substituents the lowest possible numbers with that in mind. So 3-bromoaniline, you start at 1. The shortest distance is to the bromo to give it the lowest number is going to give it the 3 position. You have 4-bromo, 2-chlorophenol. Remember, you are writing the substituents in alphabetical order without reference to prefixes, as you see in the next one, where it's 2,6-dibromo, 4-chlorotoluene. Remember, bromo precedes chloro alphabetically. The di indicating 2 bromo groups is not relevant. Okay, so it's 2,6-dibromo, 4-chlorotoluene. That's one thing that I'll bet there's going to be some mistakes on that, but pay attention to that. Oh, if let's say in the case of this 2,6-dibromo, 4-chlorotoluene, what if that chloro wasn't there? What if it were just the 2 bromines flanking the methyl group? Well, it'd be 2,6-dibromotoluene. Okay, because the methyl group is the one, it's a toluene, the methyl group is the one carbon. So, it's not 1,3. 1,3 would, well, 1,3 would be, or, well, you could, well, look at methyl is number 1, so you've got 1 bromine's on a 2 carbon, and I mean you don't go backwards, you go all the way around the ring to the 6 carbon. So I don't know if there's any problems on that, but if there are, I don't see any here. All right. We have chemistry linked to health. This is one of these. This is common aromatic compounds. You've heard of all of these, I'm sure. You might not have heard of vanillin or vanillin. Sometimes you hear vanillin, but you have heard of vanilla. and vanillin is actually in vanilla. Aspirin, that's I'm not sure that's a trade name or some name that it was given to the compound. I don't know how the name came about, but you know aspirin, you've heard of that. And acetaminophen, that's another one. TNT, 2,4,6 trinitrotoluene, it's an explosive. So toluene derivatives are fairly commonplace, and you have phenols, and acetaminophen, if you think about that, that's both a phenol and an aniline, so we're not too much worried about naming that at this point. Aspirin, it's a derivative of phenol and what we call benzoic acid. I think they talk about benzoic acid here somewhere. I remember seeing it this morning. But let's just finish up with going through some of these learning checks. Let's select the current name for each compound. You have the chlorocyclohexane, chlorobenzene, or 1-chlorobenzene. Remember, if there's one substituent on a cyclic compound, you don't need on a benzene ring. You really don't need the one. And there's a cycloalkene, and then there's another substituent somewhere. Yes, but if it's a cycloalkane or a benzene ring, a benzene, and there's only one substituent, there's no numbering. So that's an aromatic compound. It's not chlorocyclohexane. It has to be a benzene, so it's chlorobenzene. This one, it's not a toluene anymore. It has 2 methyl groups. It's not methyltoluene. Remember that. Dimethyl benzenes do have their own name. All right, I'll give you the name. It's xylene, XYLEN. Okay, that's a dimethyl benzene. You don't need to know that. You just worry about dimethyl benzene. And which one is it? Well, there's the 2 substituents. They have to have the lowest name. So one of them's going to have to be 1, and the other one's going to have to be the lowest number going around the ring. So it's going to be 1,3-dimethyl benzene. Should be fairly straightforward. So we're finished up with chapter 8, and you see the concept map here. There's a few things there that we didn't talk about. We didn't really talk about the hydrogenation and hydration, the reactions of double bonds. They can be, they undergo some reactions, and you'll see a lot of these things when we get into biochemistry. And I did say, now I recall, I did say I saw benzoic acid. Benzoic acid is when we're going to see benzoic acid when we get to carboxylic acids, which is going to be after we do alcohols, thiols, ethers, and I think amines are in that one. But we're going to be coming up. That'll be part 3. I'm going to finish this thing up. I'm going to put it on the Facebook, and then, or not Facebook, onto YouTube, and I'm going to get on with that one. So that's all for the hydrocarbons. Now we're going to get into other functional groups, other things on the carbon chain. So I'll see you on that side.